What if I told you there are objects in the universe so unimaginably bright, they outshine entire galaxies? Picture this, a single point of light, blazing with the energy of 1 trillion suns, so powerful it can be seen clear across the cosmos, even from billions of light years away. These aren't stars, they're not even supernovas. These are quasars, the universe's ultimate powerhouses, cosmic beacons so intense they defy everything we thought we knew about energy and scale. And here's the wildest part. At the heart of each one lies a secret so profound, it reshapes our understanding of space itself. For decades, quasars have been one of astronomy's greatest mysteries. Imagine something so luminous, it can outshine 1,000 Milky Ways combined, yet small enough to fit inside our solar system. How does something like that even exist? Where does all that energy come from? The answer lies in the most extreme environments in the universe, places where gravity bends space and time, where matter is stretched to its limits, and where the laws of physics as we know them are pushed to the brink. This isn't just science, this is the universe showing off, revealing its most dramatic, violent, and awe-inspiring performances. But the real magic isn't just in their brilliance, it's in what they tell us about the cosmos. Quasars are like time machines, their light traveling for billions of years before reaching us, carrying secrets from the early universe. They're clues to how galaxies form, how black holes grow, and even how the fabric of reality itself might be woven. Today, we're going on a journey to uncover the truth behind these cosmic titans, how they form, why they shine so fiercely, and what they reveal about the universe's most hidden forces. By the end, you'll see the night sky in a whole new way, not just as a tapestry of stars, but as a living, evolving story written in the language of quasars. So let's dive in. The universe's brightest secrets are waiting. At their core, quasars are the brilliant hearts of distant galaxies, but not just any galactic centers. These are cosmic furnaces fueled by something truly monstrous. Imagine a black hole so massive, it dwarfs our sun by millions or even billions of times. And then picture that black hole not as a silent void, but as a ravenous engine devouring everything in its path. This is the powerhouse behind a quasar. Gas, dust, and even entire stars spiraling into the black hole's grip at nearly the speed of light, heating up to millions of degrees and unleashing energy so intense it can outshine the combined light of every star in its host galaxy. When astronomers first detected quasars in the early 1960s, they were baffled. These points of light looked like stars but emitted strange, powerful radio waves, so they were nicknamed quasi-stellar radio sources, or quasars for short. But as telescopes improved, the truth became clear. These weren't stars at all. They were the brightest beacons in the universe, flaring from the centers of galaxies so far away. Their light had traveled for billions of years before reaching us. A single quasar can shine hundreds of times brighter than our entire Milky Way, packing that staggering luminosity into a space no larger than our solar system. To put that into perspective, think of a flashlight in a dark room. Now imagine that flashlight is so bright, it outshines every light in every city on Earth combined. That's the kind of raw, unfathomable power we're talking about. But what makes quasars even more fascinating is how they work. As matter falls toward the supermassive black hole, it doesn't just vanish. It forms a swirling disk called an accretion disk, glowing white-hot with friction. Magnetic fields twist this chaos into jets of plasma, shooting outward at nearly light speed, carving through galaxies and lighting up the cosmos like celestial fireworks. This isn't just a black hole lurking in the shadows, it's a black hole turned up to 11, a cosmic dynamo converting gravity into pure energy on a scale we can barely comprehend. And yet, quasars aren't just destructive forces, they're sculptors, shaping the galaxies around them and even influencing how stars form. They're proof that the universe isn't just a static place of quiet darkness. It's alive with energy, violence, and beauty written in the language of light. To understand a quasar's blinding brilliance, we need to dissect its anatomy layer by violent layer. At the center sits the ultimate cosmic predator, a supermassive black hole weighing millions to billions of times more than our Sun. But unlike solitary black holes lurking in darkness, this one is feasting. It's surrounded by a churning, glowing maelstrom of gas, dust, and shredded stars, a structure known as the accretion disk. Picture liquid fire spiraling down a drain, except this drain is the most extreme gravitational vortex in existence. As matter gets pulled inward, it doesn't go quietly. Particles collide, rub against each other, and heat up to temperatures hotter than the core of a star, millions of degrees. This friction doesn't just glow, it radiates light across the entire electromagnetic spectrum, from X-rays to visible light, turning the disk into a cosmic lighthouse. The closer the material gets to the black hole's event horizon, the faster it moves, approaching the speed of light, warping time and space itself. But here's where things get even wilder. Not all that doomed matter gets swallowed. Some gets channeled by the black hole's insane magnetic fields and shot back out into space in jets, twin beams of plasma traveling at nearly the speed of light. These relativistic jets can stretch hundreds of thousands of light years, punching through galaxies and intergalactic space like celestial blowtorches. What makes quasars truly unique is how all these parts work together. The black hole is the engine, the accretion disk is the fuel, and the jets are the exhaust, a cosmic power plant operating at the absolute limits of physics. And the light we see, that's the universe's most energetic savings account, converting matter into pure radiation with terrifying efficiency. Unlike stars, which shine through nuclear fusion, quasars shine by turning gravity itself into light, proving Einstein right in the most spectacular way possible. Yet for all their violence, quasars aren't random. The most luminous ones often appear in young, chaotic galaxies where fresh gas and stars provide endless fuel. Over time, as the black hole devours its surroundings and the galaxy stabilizes, the quasar dims, leaving behind a quieter, supermassive black hole like the one at the center of our Milky Way. So in a way, every quasar is both a birth cry and a death knell, marking a galaxy's fiery adolescence before it settles into maturity. If you think all cosmic light shows are created equal, think again. Quasars may be the brightest objects in the universe, but they're far from the only spectacular phenomena lighting up the cosmos. Take pulsars, for example. These spinning neutron stars are like celestial lighthouses, beaming radiation in precise pulses as they rotate. While they're incredibly dense and fast, they're mere flickers compared to the sustained, city-sized inferno of a quasar. Pulsars shine through focused beams, but a quasar, it's an all-out blaze, a relentless flood of energy pouring from its accretion disk and jets. Then there are blazars, close cousins to quasars, but with a twist. Both are powered by supermassive black holes, but blazars point one of their plasma jets almost directly at Earth, making them appear even brighter in our telescopes. Think of it like the difference between seeing a flashlight from the side versus staring straight into its beam. Blazars can flare unpredictably, their light dancing across wavelengths, while quasars burn with a more steady, colossal fury. But what about ordinary black holes, the kind that lurk silently in the centers of galaxies, like Sagittarius, a star in our Milky Way? These black holes are quasars that have run out of fuel, quiet giants no longer surrounded by enough gas to ignite that dazzling accretion disk. They're the remnants of a quasar's glory days, proof that even the brightest cosmic engines eventually dim. And then there are the sudden, violent bursts, gamma-ray explosions, and supernova. These events pack insane energy into seconds or days, briefly outshining entire galaxies. But quasars, they keep shining for millions of years, their light fueled by an endless buffet of infalling matter. A supernova is a firework, a quasar is a bonfire that never burns out. What truly sets quasars apart are those jets' narrow, focused streams of plasma moving at nearly light speed, carving through space for hundreds of thousands of light years. Gamma-ray bursts might have similar jets, but they're fleeting. Quasar jets persist, shaping their galaxies and beyond, acting like cosmic blowtorches that can ignite star formation or snuff it out. They're not just bright, they're builders, sculptors, and destroyers all at once. So next time you look up at the night sky, remember, not all light is created equal. Some cosmic objects flicker, some explode, but quasars, they dominate, outshining everything else in a display of raw power that defies imagination. To witness the birth of a quasar is to watch the universe play out its most dramatic recipe, a mix of chaos, gravity, and gluttony on an unimaginable scale. It all begins with a supermassive black hole lurking in the heart of a young galaxy like a sleeping giant. But this isn't just any black hole, it's one with an insatiable appetite, waiting for the right moment to wake up and feast. And what triggers that moment? Often it's a galactic collision, a cosmic car crash of unimaginable proportions. Picture two galaxies, each brimming with gas, dust, and stars, drifting through the void until gravity pulls them into a violent dance. As they spiral toward each other, their structures warp and shred, sending massive clouds of gas hurtling toward their central black holes. It's like shaking a soda can and then popping the tab. Suddenly, all that pent-up energy has somewhere to go. The black hole, now flooded with fresh fuel, starts devouring everything in reach, and that's when the magic, or rather, the mayhem begins. The influx of material forms a swirling, superheated disk around the black hole, so energetic it radiates more light than the rest of the galaxy combined. This isn't just a meal, it's a full-blown cosmic barbecue with matter burning at temperatures hotter than the core of a star. And the black hole doesn't just eat politely, it's messy, flinging some of its meal back out into space in those spectacular jets we see as twin beams of high-energy plasma. Simulations of the early universe show just how common these feeding frenzies must have been. Billions of years ago, galaxies were smaller, closer together, and packed with gas-perfect conditions for collisions and quasar formation. Some of the brightest quasars we see today are actually relics of this era, their light traveling for eons before reaching us. They're like distant fireworks frozen in time, showing us what happens when galaxies collide and their black holes wake up hungry. But here's the kicker, quasars don't just light up the cosmos, they shape it. The energy they blast out can blow away surrounding gas, shutting down star formation in their host galaxies. It's a cosmic irony. The same process that fuels a quasar can also starve its galaxy of the material needed to make new stars. Over time, as the black hole runs out of food, the quasar fades, leaving behind a quieter galaxy with a bloated, dormant black hole at its center. So the next time you hear about a quasar, remember, you're not just looking at a bright light in the sky. You're seeing the aftermath of a galactic wreck, a black hole's feast, and a turning point in a galaxy's life. It's a reminder that even in the vastness of space, nothing stays still, not even the universe's brightest monsters. The accretion disk around a supermassive black hole isn't just a flat, spinning pancake of matter. It's a seething, violent whirlpool where physics gets pushed to its breaking point. Imagine a cosmic hurricane, but instead of wind and rain, it's made of superheated gas and plasma, swirling at speeds approaching half the speed of light. The closer you get to the black hole's event horizon, the more extreme it becomes, with temperatures soaring to millions of degrees, hot enough to strip atoms apart and turn matter into a glowing, radioactive soup. But here's the catch, this disk isn't uniform. It's layered like an onion, with each ring behaving differently based on its distance from the black hole. The outer edges are cooler, maybe just thousands of degrees, where gas and dust still cling together in thicker clumps. As material spirals inward, though gravity's grip tightens, collisions between particles become more frequent, and friction heats everything to unimaginable temperatures. By the time matter reaches the innermost orbits, it's not just hot. It's emitting X-rays and gamma rays, transforming the disk into one of the most energetic light factories in the universe. Magnetic fields play a starring role in this chaos. They're not just passive bystanders, they're active sculptors, twisting and stretching the disk's plasma into towering loops and filaments. These fields act like cosmic dynamos, channeling some of the infalling matter away from the disk and launching it into those relativistic jets we see shooting out from the poles. Without these magnetic forces, a quasar's brilliance would be dimmed, its jets stifled, its energy less focused. Yet even with all this chaos, there's a limit to how much a black hole can devour. Enter the Eddington limit, a sort of cosmic speed bump for black hole feasting. Named after astrophysicist Arthur Eddington, it's the maximum rate at which a black hole can consume matter before the radiation it produces becomes so intense that it literally pushes back on incoming material, like a star's light holding back a solar sail. Beyond this limit, the sheer energy radiating from the disk blows away any new fuel, starving the black hole until balance is restored. It's nature's way of saying enough. This delicate dance between gravity pulling matter in and radiation pushing it away creates the quasar's signature brilliance. Too little fuel and the black hole goes dark. Too much and it chokes on its own glow. But when conditions are just right, when the accretion disk hums at the perfect equilibrium, the result is a beacon so bright it can outshine galaxies. That's the secret behind a quasar's power, not just a voracious black hole, but a masterfully tuned cosmic engine burning at the edge of what physics allows. Those relativistic jets screaming out from quasars aren't just cosmic fireworks, they're nature's ultimate particle accelerators, hurling matter across the universe at speeds so close to light, the laws of physics start to warp. Picture a black hole not just as a silent vacuum, but as a cosmic slingshot, launching jets of supercharged plasma hundreds of thousands of light years into intergalactic space. These aren't gentle streams, they're torrents of ionized gas hotter than a supernova, channeled by magnetic fields so intense they could rip atoms apart. So how does a black hole, an object famous for sucking everything in, manage to blast so much material outward? The answer lies in a brilliant cosmic balancing act. As matter spirals into the black hole's accretion disk, it drags magnetic field lines along with it, twisting them into knots of unimaginable energy. Think of it like winding up a rubber band until it snaps, except here, the rubber band is space-time itself, and the snap unleashes enough power to launch jets at nearly light speed. This is the heart of the Blandford-Zenagic process, a theory that explains how black holes convert rotational energy into these terrifyingly efficient cosmic railguns. But here's the twist: the black hole isn't doing all the work alone. The accretion disk acts like a collaborator, feeding the black hole's spin while magnetic fields act as invisible highways, guiding some of that infalling matter away from oblivion and redirecting it into the jets. It's as if the black hole is sipping its meal through a straw while simultaneously spitting some of it back out in focused, high-energy bursts. And these jets aren't just random ejections, they're precision-engineered, often aligning with the black hole's poles like twin geysers of raw cosmic power. What's truly mind-blowing is the scale. These jets can stretch far beyond their host galaxies, carving through intergalactic space and plowing into neighboring gas clouds. When they collide, they trigger shockwaves that heat surrounding material to millions of degrees, creating vast bubbles of radio emission that glow across the cosmos. In some cases, these jets even act like cosmic gardening tools, compressing gas clouds and sparking the birth of new stars, proof that destruction and creation in the universe are often two sides of the same coin. Yet for all their violence, relativistic jets are also cosmic messengers. By studying their light polarization and how they interact with their surroundings, astronomers can decode the secrets of the black holes that launch them. The jet's stability over such vast distances hints at the precision of the underlying physics, while their occasional flares and kinks reveal the turbulent dance of matter and magnetism near the event horizon. They're not just byproducts of a quasar's power, they're the universe's way of broadcasting the extreme physics at its heart. The light we see from quasars today isn't just a signal from deep space, it's a message from deep time. Because these cosmic beacons are so mind-bendingly distant, their light takes billions of years to reach us, meaning every quasar we observe is a snapshot of the universe's past. Imagine looking at a photograph of your grandparents as children. That's essentially what astronomers do when they study quasars. These objects aren't just bright, they're time capsules holding secrets from an era when galaxies were young, the cosmos was denser, and black holes were feasting on a universe still rich with fuel. To understand how this works, think of light as a cosmic postcard. When a quasar emits a burst of radiation, that light travels across the universe, stretching and shifting as it goes. By the time it reaches Earth, its wavelength has been stretched or redshifted by the expansion of space itself. The farther away the quasar, the more extreme this redshift becomes, like a tape recording playing slower and slower. Scientists measure this shift to calculate not just the quasar's distance, but also how long its light has been journeying through the void. Some of the most distant quasars we've detected have redshift so high, their light left them when the universe was less than 1 billion years old, a mere fraction of its current age. But quasars don't just tell us when they existed, they reveal what the early universe was like. Their light passes through clouds of gas and dust on its way to us, absorbing specific wavelengths that act like chemical fingerprints. By decoding these absorption lines, astronomers can map the distribution of matter across cosmic time, tracing how the universe evolved from a dense, opaque soup of hydrogen into the structured web of galaxies we see today. It's like analyzing sunlight filtered through a stained glass window. Each color tells a story about what it passed through. What's even more astonishing is how quasars expose the infancy of supermassive black holes. The fact that we see these monsters already fully grown in the early universe challenges our theories about how they formed so quickly. Did they start as colossal seeds born from the collapse of giant gas clouds? Or did they balloon in size by merging with other black holes in a violent cosmic feeding frenzy? Quasars are the only witnesses to this ancient drama, and their light holds the answers. And here's the kicker: because space itself is expanding, the most distant quasars are being carried away from us faster than their light can reach Earth. Eventually, their light will fade from view entirely, leaving future astronomers in the dark about the universe's fiery youth. We're living in a golden age of cosmic observation, where these primordial beacons are still visible if we know how to look. So every quasar we study isn't just a distant object, it's a fleeting whisper from the dawn of time, reminding us that the night sky isn't just a place, it's a story written in light older than Earth itself. Dark matter, the universe's invisible scaffolding, might just be the hidden architect behind quasars' monstrous appetites. While we can't see it directly, its gravitational fingerprints are everywhere, shaping galaxies into vast, swirling disks and holding them together with an unseen hand. But here's the twist: dark matter doesn't just keep galaxies from flying apart, it might also be the reason some of them become cosmic lighthouses in the first place. Picture a galaxy wrapped in a colossal, ghostly cocoon, a halo of dark matter stretching far beyond its visible stars. This halo's gravity acts like a cosmic funnel, pulling in streams of gas from intergalactic space and directing them toward the galaxy's center. When enough gas piles up near the supermassive black hole lurking there, the feast begins, igniting the quasar's dazzling accretion disk. Without these dark matter halos, galaxies might struggle to gather enough fuel to power such extreme brilliance. Yet mysteries remain. If dark matter is everywhere, why don't all galaxies light up as quasars? The answer might lie in the chaotic dance of galactic collisions. When two galaxies merge, their dark matter halos intertwine, stirring up gas and sending shockwaves of material spiraling toward their central black holes. This could explain why quasars often flare to life during these violent encounters, like striking a match in a room filling with gas. But some galaxies, even those with hefty dark matter halos, remain quiet. Perhaps their black holes are picky eaters, or maybe their gas supply is locked away in stable orbits, refusing to fall inward. Another puzzle: why do some quasars flicker out after just a few million years, while others burn for hundreds of millions? Dark matter's role here is still hazy. Some theories suggest the halo shapes, whether lumpy or smooth, could control how efficiently gas streams toward the center. Others propose that magnetic fields or turbulence in the galactic core might disrupt the flow, starving the black hole even in the presence of abundant fuel. One thing's certain: dark matter isn't just a passive backdrop. It's an active player in the universe's most energetic phenomena, orchestrating the rise and fall of quasars with invisible hands. And as astronomers peer deeper into the cosmos, they're finding clues that the brightest objects in the universe might owe their existence to the darkest substance we know. The next time you hear about a quasar's brilliance, remember, it's not just the black hole's doing. It's the unseen halo, the silent puppeteer pulling the strings behind the scenes. Quasars may burn with the fury of 1 trillion suns, but even the universe's brightest monsters can't shine forever. Their brilliance isn't infinite. It's a temporary blaze fueled by a black hole's insatiable appetite, and like all feasts, it eventually ends. The reason: cosmic starvation. A quasar's light depends on a steady supply of gas, dust, and stars falling into its accretion disk. But over time, the black hole devours everything within reach or flings it away in those powerful jets. Without fresh fuel, the disk thins, the jets sputter, and the quasar dims from a roaring inferno to a faint ember, a process that can take millions, even billions of years. Take our own Milky Way as an example. At its heart sits Sagittarius, a star, a supermassive black hole over 4 million times heavier than our Sun. But unlike a quasar, it's not lighting up the galaxy, it's dormant, a sleeping giant. Why? Because our galaxy is orderly, its gas settled into stable orbits with little free material falling inward. The black hole isn't starving, it's just waiting. Occasionally, it might snack on a passing cloud or a stray star, flaring briefly like a match struck in the dark, but these moments are fleeting. Our Milky Way's quiet center isn't a flaw, it's a sign of cosmic maturity, a galaxy that's moved past the chaotic, gas-rich adolescence that births quasars. But how does a quasar's host galaxy transition from chaos to calm? It's a combination of exhaustion and expulsion. As the black hole feasts, its radiation and jets push away nearby gas, clearing out the neighborhood like a cosmic hurricane. Star formation slows as the galaxy's fuel reserves dwindle, either consumed or blown into intergalactic space. Over time, without fresh material to spiral inward, the accretion disk fades and the quasar's light dims. The once dominant black hole becomes a quiet monarch, its reign of brilliance over, its galaxy settling into a quieter, more stable phase. There's poetic symmetry to it. A quasar's death is as dramatic as its birth. The same forces that made it shine, gravity, friction, and magnetism, eventually conspire to silence it. And while the universe still hosts active quasars in younger, gas-rich galaxies, their days are numbered too. Each one is a temporary beacon, a flare in the cosmic night, reminding us that even the most violent, radiant phenomena are just chapters in a much larger story. The Milky Way's quiet center isn't an anomaly, it's a glimpse of the future for every quasar-lit galaxy, a testament to the universe's relentless cycle of chaos and calm. Among the countless quasars scattered across the cosmos, a few stand out not just for their brilliance, but for pushing the limits of what we thought was possible. Take Euler's J1342 + 0928, the most distant quasar ever discovered. Its light traveled for over 13 billion years to reach us, meaning we're seeing it as it was when the universe was a mere 700 million years old, a cosmic toddler. This isn't just a record breaker, it's a time machine offering a glimpse into an era when the first galaxies were still assembling and the universe was emerging from its dark ages. What's astonishing isn't just its distance, it's the fact that it hosts a supermassive black hole already weighing in at 800 million times the mass of our Sun. How did something so colossal form so quickly after the Big Bang? That's a puzzle scientists are still trying to solve. Then there's SDSS J0100 plus 2802. A quasar so luminous it outshines our Sun by 420 trillion times. To put that into perspective, if you place this quasar where our Sun sits, its glare would vaporize Earth in an instant. What makes it even more remarkable is its black hole, a staggering 12 billion solar masses, one of the heaviest ever measured. It's like finding a sumo wrestler in a nursery. This thing defies expectations, challenging our understanding of how black holes grow. But size and distance aren't the only records quasars break. Some, like APM 08279 plus 5255, are speed demons, blasting out material at 99.9% the speed of light, so close to the universe's ultimate speed limit, you'd need a microscope to spot the difference. Others, like 3C273, double as cosmic art galleries, their jets sculpting vast lobes of radio emission that stretch millions of light years, painting the sky with invisible brushstrokes of energy. What ties these extreme quasars together isn't just their terrifying stats, it's what they reveal about the universe's most violent epochs. They're proof that the cosmos didn't ease into maturity. It exploded onto the scene, with black holes growing at breakneck speeds and galaxies igniting in bursts of light. And while these record holders are rare, each one is a Rosetta Stone, helping astronomers decode the universe's most turbulent chapters. Quasars aren't just cosmic light shows, they're galactic engineers shaping the very galaxies they call home in ways we're only beginning to understand. One of the most fascinating theories in modern astrophysics is the idea that quasars act as cosmic regulators, using their incredible energy output to control how many stars their host galaxies can form. It sounds counterintuitive. How could something so destructive create order? But the evidence is mounting, and it all comes down to something called quasar feedback. Picture a galaxy brimming with gas, the raw material needed to build new stars. Left unchecked, this gas would collapse under gravity, sparking a frenzy of star birth. But when a quasar ignites at the galaxy's core, its jets and radiation blast outward like a cosmic hurricane, sweeping up surrounding gas and pushing it far beyond the galaxy's reach. This isn't a gentle nudge, it's a galactic-scale wind capable of reaching speeds of thousands of kilometers per second, carrying away enough material to build millions of stars. The result, a galaxy that's effectively put on a diet, starved of the fuel it needs to keep forming new stellar generations. Astronomers have caught this process in action. Observations with telescopes like Hubble and the Atacama Large Millimeter Array reveal massive outflows of gas streaming away from quasars, some stretching tens of thousands of light years. These aren't quiet leaks, they're explosive ejections with enough energy to reshape entire galaxies. In some cases, the winds are so powerful, they can strip a galaxy of its gas reservoir in just a few million years, a blink of an eye in cosmic terms. But here's the twist. While this feedback might sound purely destructive, it's also a form of cosmic balance. Without quasars clearing out some of this gas, galaxies might burn through their fuel too quickly, forming stars in unsustainable bursts before sputtering out. By regulating star formation, quasars could be ensuring their host galaxies evolve steadily, avoiding early burnout. It's like a forest fire, devastating in the moment but necessary to clear the way for new growth. The most striking evidence comes from galaxies that appear to have shut down star formation entirely. These red and dead galaxies, so called because they're filled with aging red stars and lack the blue glow of young stellar nurseries, often show signs of past quasar activity. Their black holes may now be quiet, but the scars of their outbursts remain ghostly echoes of winds that once blew with enough force to halt star birth across an entire galaxy. This feedback loop isn't just a one-way street. As quasars influence their galaxies, the galaxies, in turn, influence their quasars. When gas blown away by feedback eventually cools and falls back toward the galactic center, it can reignite the black hole's appetite, triggering new quasar activity. It's a self-regulating cycle, violence and calm, feasting and fasting, playing out over billions of years. So the next time you hear about a quasar's incredible brilliance, remember, it's not just a beacon. It's a sculptor, a destroyer, and a guardian all at once, wielding its energy not just to shine, but to shape the destiny of its galactic home. Far from being passive bystanders, quasars might be the universe's way of ensuring galaxies don't just live fast and die young, but instead evolve into the stable, structured cosmic cities we see today. To truly understand quasars, we need more than just raw power, we need precision. That's where our most advanced telescopes come in, each acting like a specialized translator for the universe's brightest enigmas. Take Chandra, for example. This X-ray observatory orbits high above Earth's atmosphere, capturing the highest energy light streaming from quasars' light that will be completely invisible to our eyes. Why does that matter? Because the innermost regions of a quasar's accretion disk, where temperatures soar to millions of degrees, glow brightest in X-rays. Chandra's sharp vision lets us peer into this extreme environment, revealing how matter behaves just before it vanishes beyond the event horizon. Without it, we'd be missing half the story, like trying to study a fire by only seeing the smoke. Then there's Hubble, the iconic telescope that brought us stunning visible light portraits of quasars and their host galaxies. While Hubble can't see the searing X-rays from the disk's heart, it captures something equally vital, the quasar's broader structure. Its crisp images show how these brilliant cores are embedded within distant galaxies, often revealing the tangled aftermath of galactic collisions, the very chaos that feeds the black hole's frenzy. Hubble also spots the quasar's impact on its surroundings, like glowing gas clouds illuminated by its radiation or star-forming regions disrupted by its jets. It's the cosmic equivalent of a wide-angle lens, giving us context for the violence at the center. But to hear the universe's whispers, we turn to ALMA, an array of radio telescopes in the high deserts of Chile. While Chandra and Hubble show us the fury, ALMA listens to the echoes. Quasars don't just emit visible light and X-rays. Their jets blast out radio waves, and the cold gas swirling around them absorbs specific frequencies like a cosmic fingerprint. ALMA antennas working in unison detect these subtle signals, mapping the distribution of molecules like carbon monoxide across thousands of light years. This tells us what quasars are made of and how they interact with their galactic neighborhoods. It's like putting a stethoscope to the cosmos, hearing the heartbeat of gas swirling toward oblivion. Yet none of these tools would mean much without spectroscopy, the real game changer in quasar research. When astronomers split a quasar's light into a rainbow of wavelengths, dark lines appear in the spectrum, each representing atoms that absorbed specific colors along the light's journey. These lines act as barcodes, revealing the composition, temperature, and even motion of the gas between us and the quasar. Some lines are shifted toward the red end of the spectrum, proof the universe is expanding, stretching the light as it travels. Others show telltale signs of elements like hydrogen, helium, and iron, painting a picture of the chemical universe billions of years ago. Spectroscopy turns light into a time machine, letting us dissect quasars atom by atom across cosmic time. Combined, these instruments form a symphony of observation. Chandra spots the black hole's fiery breath, Hubble frames its galactic home, ALMA traces its cold fuel reserves and spectroscopy deciphers its ancient light. Together, they reveal quasars not as static points of light, but as dynamic engines, cosmic laboratories where gravity, magnetism, and radiation collide in the most spectacular ways imaginable. And with next-generation telescopes like the James Webb Space Telescope joining the hunt, we're on the verge of uncovering even deeper secrets, like how the very first quasars ignited in the universe's infancy and what they can teach us about the origins of everything. The tools are here, the universe is talking, all we have to do is listen. Not all quasars shine the same way. Some beam their light directly at us, while others hide behind thick cosmic curtains. The differences come down to perspective and physics, creating distinct classes that astronomers call Type 1 and Type 2 quasars. Picture standing in front of a lighthouse. If you're facing the beam head-on, the light is blinding. That's a Type 1 quasar. Its accretion disk and jet point toward Earth, giving us an unobstructed view of its searing core, complete with broad emission lines in its spectrum from gas swirling at insane speeds. Now imagine viewing that same lighthouse from the side, where the beam is hidden behind the tower's walls. That's a Type 2. Its central engine is obscured by a donut-shaped ring of dust, filtering its light into narrower spectral lines and muting its brilliance. The crazy part, these might be the exact same object, just seen from different angles, proof that cosmic perspective changes everything. But orientation isn't the only thing that splits quasars into categories. Some are loud, blasting out radio waves from jets that rip across galaxies, while others are quiet, glowing fiercely but without the same explosive outflows. The loud ones, called radio-loud quasars, are the rock stars of the cosmos, their jets acting like interstellar amplifiers. Then there are the show-offs, blazars, a subtype of radio-loud quasars that point their jets almost directly at us. Staring down the barrel of a blazar's beam is like looking into a cosmic blowtorch, their light amplified by relativistic effects to outshine even ordinary quasars. On the flip side, radio-quiet quasars still pack immense power, but their energy spills out more evenly, like a light bulb instead of a laser. Why does this variety exist? It all traces back to the black hole's messy eating habits. In some galaxies, magnetic fields focus the chaos into tight jets, creating radio-loud monsters. In others, the gas might spiral in more chaotically, like water circling a drain without a splash, producing radio-quiet but still dazzling beacons. Throw in the random luck of whether Earth lies in the path of a jet, and you've got a full quasar zoo, each specimen revealing a different facet of these cosmic beasts. The next time you hear about a quasar's brilliance, remember, what we see depends on where we're standing in the universe's grand, spinning theater. Quasars have inspired wild theories over the years, from whispers of alien gateways to fears they might swallow our solar system whole. Let's set the record straight. First, the idea that quasars are cosmic portals or doorways to other dimensions makes for great sci-fi, but it's pure fantasy. These objects aren't mystical vortices, they're natural phenomena governed by the same physics as everything else in the universe. Their mind-bending energy comes from superheated gas, not some interdimensional rift. And while their jets do stretch across incomprehensible distances, they're made of ordinary matter, just accelerated to extreme speeds by magnetic fields and gravity. Now about those doomsday fears. Could a quasar's jet or radiation ever reach Earth? Not a chance. The nearest known quasars are billions of light-years away, so distant that even their unimaginable power is diluted to a faint flicker by the time it reaches us. To put it in perspective, if our sun suddenly turned into a quasar, which it absolutely couldn't, we'd be vaporized instantly, but at their actual distances. They're no more threatening than a candle on the other side of a continent. Even if one pointed directly at us, the universe's vastness is our best shield. Some people hear supermassive black hole and assume quasars are vacuuming up galaxies like cosmic hoovers, but black holes, even the hungriest ones, aren't all-consuming voids. Their gravity is only unstoppable if you get too close, like within the event horizon. Outside that point, stars and gas can orbit them just as planets orbit our sun. A quasar's glow comes from matter avoiding immediate destruction, swirling in the accretion disk for thousands of years before slipping over the edge. Then there's the myth that quasars are rare. They're not, they're just usually ancient. Most existed during the universe's early, crowded epochs when galaxies collided frequently and black holes had endless fuel. Today, they're rarer because the cosmos has expanded, leaving less gas for feasting. But they're still out there, hidden in distant galaxies or disguised as quieter active nuclei. So why study them if they pose no threat? Because quasars are cosmic Rosetta Stones. Their light carries encoded details about the universe's youth, the composition of early matter, the growth of galaxies, even the nature of spacetime itself. Without quasars, we'd know far less about dark matter's role in shaping the cosmos or how black holes evolve. Far from being terrifying, they're some of our greatest teachers, proving that the universe's most violent acts can also be its most illuminating. The next time you hear an outlandish quasar theory, just remember, reality is far more fascinating than fiction. These objects don't need embellishment to awe us. Their sheer scale, power, and role in cosmic history are spectacular enough. Quasars do more than dazzle. They illuminate the hidden architecture of the cosmos like celestial lighthouses, piercing through the darkness to reveal the universe's grand design. Their light doesn't just travel straight to us, it passes through vast clouds of intergalactic gas, leaving behind fingerprints that astronomers decode to map the universe's scaffolding. One of the most powerful tools for this cosmic cartography is something called the Lyman Alpha Forest. The name sounds whimsical, but the science is profound. When a quasar's ultraviolet light journeys through space, it encounters hydrogen gas clouds floating between galaxies. Each cloud absorbs a specific wavelength of light, known as the Lyman Alpha line, creating a series of dark absorption lines in the quasar's spectrum. The result, a forest of lines, each representing a different gas cloud at a unique distance along the line of sight. It's as if the quasar's light is a beam passing through layers of stained glass, with each pane leaving its own colored shadow. But this isn't just about pretty patterns, it's a goldmine of information. By analyzing these absorption lines, scientists can reconstruct the distribution of matter across billions of light years. The closer the lines are packed together, the denser the gas in that region of space. Some reveal vast, thread-like structures, cosmic filaments that weave the universe into a web-like framework, where galaxies cluster like dewdrops on a spider's silk. Others expose enormous voids, deserts of near-empty space stretching for hundreds of millions of light years. Together, they form a three-dimensional atlas of the universe's large-scale structure, all painted in the quasar's borrowed light. What's even more remarkable is how these absorption lines act as time capsules. Because light takes time to reach us, the Lyman Alpha Forest captures snapshots of the universe at different epochs. The most distant quasars show forests with thicker, more crowded lines, evidence of a younger cosmos filled with denser gas. As we look closer, the lines thin out, reflecting the universe's expansion and the gradual clearing of intergalactic space as galaxies formed and stars ignited. It's like peeling back layers of an archaeological dig, where each stratum tells a story about how the universe evolved from a primordial soup into the structured expanse we see today. Quasars also serve as backlights for studying the elusive intergalactic medium, the diffuse gas that fills the space between galaxies. This material is so tenuous it's nearly invisible on its own. But when a quasar's light shines through it, the gas betrays its presence by absorbing specific wavelengths. By measuring the exact positions and depths of these absorption lines, astronomers can determine not just where the gas is, but also its temperature, density, and even its motion. Some clouds are racing toward us, others speeding away, tracers of the universe's turbulent flows, like leaves caught in a cosmic river. The real magic happens when quasars and their Lyman alpha forests are combined with modern sky surveys. Projects like the Sloan Digital Sky Survey have mapped hundreds of thousands of quasars, turning their absorption lines into a statistical powerhouse. By stacking data from multiple sources, scientists can detect patterns too faint to see in any single spectrum, revealing the universe's skeleton in unprecedented detail. It's like assembling a jigsaw puzzle where every quasar adds another piece, gradually uncovering the full picture of how matter is woven across the cosmos. Far from being isolated beacons, quasars are collaborative cartographers, their light stitching together a map of the universe's past and present. Without them, we'd be stumbling in the dark, blind to the invisible structures that shape everything we see. They remind us that the night sky isn't just a scattering of stars. It's a dynamic, interconnected web, and quasars are the threads that help us trace its design. The sheer brilliance of a quasar defies common sense. How can something so compact radiate more energy than entire galaxies? The secret lies in an astronomical alchemy that turns gravity itself into light with staggering efficiency. While stars like our Sun generate energy through nuclear fusion, converting just 0.7% of their mass into energy, quasars operate on a whole different level. The supermassive black hole's accretion disk achieves efficiencies up to 40%, making it the universe's ultimate power plant. Imagine tossing a lump of coal into a furnace. It burns, releasing energy trapped in its chemical bonds. Now imagine dropping that same lump into a black hole's accretion disk. As it spirals inward, friction heats it to millions of degrees, while intense gravity squeezes every joule of potential energy from its mass. But unlike a furnace that burns fuel unevenly, the disk operates like a perfectly tuned machine, converting matter into radiation with almost industrial precision. The closer the material gets to the event horizon, the faster it moves, approaching light speed and releasing energy across the entire electromagnetic spectrum: X-rays, gamma rays, visible light. It's not just heat, it's raw spacetime itself being twisted into energy. This process dwarfs even the most powerful stars. Nuclear fusion, which powers our Sun, relies on mashing hydrogen atoms together to form helium, a reaction that leaves most of the original mass untouched. But in a quasar's accretion disk, nothing goes to waste. The disk's magnetic fields churn the plasma like a cosmic dynamo, while gravitational energy gets extracted with ruthless efficiency. Some of that energy fuels the jets blasting outward at near light speed. The rest floods the universe in a continuous blaze of radiation. What makes this even more astonishing is the scale. A single kilogram of matter falling into a quasar's disk releases energy equivalent to detonating millions of nuclear bombs. Now picture billions of tons of gas and stars plunging inward every second. That's the kind of math that explains how quasars outshine galaxies. And unlike stars, which eventually run out of fuel, quasars can keep shining for millions of years as long as fresh matter keeps feeding the disk. Yet even quasars have limits. Push the infall rate too high and radiation pressure starts blowing material away, choking off the black hole's meal. It's a self-regulating system, balancing gluttony against its own brilliance. Nature's way of ensuring these cosmic monsters don't burn out too soon. When you grasp the physics behind their light, quasars stop being mere oddities. They become masterclasses in energy conversion, proving that gravity, not fusion, is the universe's most relentless power source. Peering into the heart of a quasar isn't something astronomers can do first, and these cosmic beacons are too distant, too violent, and too extreme for any probe to visit. Instead, scientists rely on the next best thing: supercomputer simulations that recreate the chaos of supermassive black holes in staggering detail. Enter ENSO, one of the most advanced astrophysical codes ever developed, designed to simulate the birth and evolution of quasars by breaking down the universe into billions of digital cells. Each cell calculates the interplay of gravity, gas dynamics, radiation, and magnetic fields, a computational ballet that requires some of the world's fastest machines to perform. But simulating a quasar isn't like rendering a galaxy collision or a supernova. The physics here operates at the edge of what's possible, where space-time twists into knots and magnetic fields become cosmic particle accelerators. One of the biggest challenges, capturing the formation of those relativistic jets, the narrow, lightning-fast beams of plasma that quasars fire into intergalactic space. In reality, these jets emerge from the black hole's poles, channeled by magnetic fields that spiral tighter than a corkscrew. But in simulations, even tiny errors in modeling those magnetic fields can turn a focused jet into a chaotic spray, like a fire hose with no nozzle. Teams spend months tweaking algorithms just to stabilize these digital jets, ensuring they match the pencil-thin structures we observe in telescopic images. Then there's the problem of scale. A quasar's accretion disk might span the distance from the Sun to Pluto, while its jets stretch millions of light-years, a range so vast no single simulation can capture it all. Astrophysicists tackle this by nesting simulations within simulations, like a set of Russian dolls. A high-resolution inner box tracks the turbulent disk and the black hole's immediate surroundings, while broader, lower-resolution grids handle the jet's epic journeys. It's a bit like filming a movie with a macro lens for close-ups and a drone for sweeping landscapes, then stitching the footage together seamlessly. Magnetic fields add another layer of complexity. In a quasar's disk, these fields aren't just static lines, they're dynamic, braided threads that store and release energy like cosmic rubber bands. Simulating their behavior requires solving equations that even supercomputers struggle with, often forcing researchers to make educated guesses about how tangled these fields become. Some of the most groundbreaking runs suggest that without magnetic fields threading the disk like invisible wires, quasars might never launch jets at all. Instead, their energy would spill out in all directions like steam from a boiling pot with no lid. The payoff for these computational headaches is immense. By comparing simulations to real quasar observations, scientists can reverse engineer mysteries like how black holes grow so quickly in the early universe, or why some quasars flicker unpredictably while others shine steadily. Each run is a virtual experiment testing theories that would otherwise remain untouchable, and as supercomputers grow faster and codes like ENSO more sophisticated, these digital quasars are inching closer to reality, pixel by pixel, equation by equation. What's emerging is a revelation. Quasars aren't just random acts of cosmic violence. Their brilliance follows rules written in the language of turbulence, magnetism, and gravity, waiting to be decoded by the right simulation. Every time a supercomputer crunches through another quasar model, it's not just solving equations, it's replaying the universe's most dazzling light shows frame by frame, in the pursuit of understanding how darkness can birth the brightest objects in existence. Long before the first stars flickered to life, the universe was a vast, opaque sea of neutral hydrogen, a fog so thick not a single photon could pierce it. This was the cosmic dark ages, an era stretching from about 380,000 years after the Big Bang until nearly 1 billion years later, when the cosmos was utterly black. But then something extraordinary happened. Quasars, those brilliant beacons powered by ravenous black holes, began to flood the universe with their fierce radiation, tearing apart the hydrogen fog atom by atom in a process known as reionization. Picture the early universe like a frozen lake at dawn. The hydrogen atoms are the ice and the quasars are the rising sun, their ultraviolet light melting the frost away. But this wasn't a gentle thaw, it was a violent upheaval. The quasar's high-energy photons slammed into those hydrogen atoms like bullets, stripping away their electrons and transforming the cosmos from a dense, light-blocking soup into the transparent expanse we see today. This was the universe's great awakening, the moment it stepped out of darkness and into light. The timing of this transformation is crucial. For hundreds of millions of years after the Big Bang, the universe was too cold and too quiet for anything but hydrogen and helium. Then, as the first galaxies formed, their supermassive black holes ignited into quasars, flooding space with enough radiation to ionize the surrounding gas. But here's the twist: quasars didn't act alone. Young, massive stars contributed too, their ultraviolet light also chipping away at the hydrogen fog. Together, they lifted the cosmic veil, making the universe transparent to starlight for the very first time. Evidence of this epic reshuffling is etched into the light of quasars themselves. When astronomers study the spectra of the most distant quasars, those whose light has traveled for over 13 billion years, they find a telltale signature: patches where the hydrogen absorption lines abruptly disappear. These gaps, known as the Lyman alpha troughs, mark the bubbles of ionized gas carved out by reionization, like holes punched in a cosmic blanket. The farther back we look, the more opaque the universe becomes, until eventually the troughs vanish entirely, proof that we've reached the era before reionization began. But reionization wasn't uniform. Some regions of the universe cleared early, thanks to clusters of bright quasars and star-forming galaxies, while others lagged behind, still shrouded in hydrogen fog. Think of it like ice melting on a lake. Some patches thin faster, leaving a mosaic of open water and lingering frost. This patchwork makes reionization one of the most complex puzzles in cosmology, with quasars as the dominant but not solitary sculptors of the universe's transparency. The legacy of this upheaval is all around us. Without reionization, the universe would still be a murky void, its galaxies and stars hidden behind an eternal hydrogen curtain. The fact that we can see the cosmic microwave background, the light from distant quasars, or even the glow of our own Milky Way, is a direct result of quasars and their stellar allies burning away the cosmic fog. They didn't just light up the early universe, they gave it a window, one we're still peering through today, billions of years later. The mystery of how supermassive black holes grew so quickly, some reaching billions of solar masses when the universe was barely a toddler, has astronomers locked in one of cosmology's most heated debates. At the center of the puzzle is an almost absurd timeline. We've spotted quasars shining brightly just 700 million years after the Big Bang, meaning their black holes had to bulk up at breakneck speeds. How two competing theories dominate the conversation, each with its own tantalizing clues and frustrating gaps. The first theory suggests these black holes started life as direct collapse black holes, born from the gravitational collapse of primordial gas clouds that never fragmented into stars. Picture the early universe as a vast nursery of pure hydrogen and helium gas. Under normal conditions, such clouds would cool, break apart, and form the first generation of stars. But in rare patches where gas couldn't cool efficiently, perhaps due to intense ultraviolet radiation from nearby galaxies, these clouds would bypass star formation entirely, collapsing directly into black holes weighing tens or even hundreds of thousands of solar masses. These cosmic behemoths would then serve as ready-made seeds, giving supermassive black holes a head start on their growth spurt. Simulations show this scenario could work, but there's a catch. The conditions had to be just right, with pristine gas and the perfect balance of heating and cooling. Too much turbulence or metal contamination, and the cloud would fragment into stars instead. On the other side of the debate are those who argue for humbler beginnings, stellar mass black holes left behind by the deaths of the first stars. These early stars, known as population 3 stars, were unlike anything in today's universe. behemoths hundreds of times more massive than our Sun, burning hot and fast before exploding as supernova. Their remnants could have formed black holes a few dozen times the Sun's mass, which then grew via mergers and accretion. The problem, even under ideal conditions, it's hard to see how these small seeds could devour enough material to reach supermassive status in just a few 100 million years. They'd need to feast near continuously at the maximum theoretical rate, a gluttony that defies what we know about how gas behaves in young galaxies. A wild-card theory bridges the gap. Black hole seeds might have benefited from a cosmic buffet of dense gas and frequent mergers in the crowded early universe. Imagine a young galaxy teeming with stellar mass black holes, their orbits decaying until they collide and merge, snowballing into larger objects. Add in a steady inflow of cold gas from cosmic filaments, the universe's hidden plumbing system, and you've got a recipe for rapid growth. Some models even suggest that early black holes could have experienced super-Eddington accretion, briefly exceeding the normal limits of consumption as gas poured in faster than radiation could push it away. The stakes are high because quasars aren't just cosmic oddities, they're probes of the universe's formative years. If direct collapse seeds dominated, it would imply a universe where gas flowed smoothly into massive reservoirs, untouched by the messy fragmentation of stars. If stellar seeds won out, it would mean the first stars were even more extreme than we thought, their death seeding black holes with just enough mass to kickstart a feeding frenzy. Right now, the verdict is still out. Future telescopes like the James Webb Space Telescope and the upcoming Laser Interferometer Space Antenna might finally spot these infant black holes in their cribs, revealing whether they were born giants or grew from humble beginnings through sheer cosmic determination. Until then, the quasar origin story remains one of astronomy's greatest cliffhangers. Quasars aren't just cosmic light shows they're some of the most rigorous laboratories for testing Einstein's theory of general relativity. These extreme environments where gravity warps spacetime to its limits let astronomers probe predictions that would be impossible to study anywhere else. Take gravitational lensing, for instance. When a quasar's light passes near a massive galaxy or cluster on its way to Earth, the intervening object's gravity bends the light like a lens, creating multiple images or even smearing the quasar into a glowing arc. The effect is like holding a magnifying glass up to a distant candle, except here, the lens is made of pure spacetime curvature. By measuring how quasars split and distort, scientists can map the distribution of dark matter in the lensing galaxy, weigh distant black holes, and even test whether gravity behaves exactly as Einstein predicted across cosmic scales. But lensing is just the start. Quasars also put relativity's stranger effects on full display, like frame dragging. The mind-bending phenomenon where a spinning black hole literally twists the fabric of spacetime around it like a spoon stirring honey. Near a quasar's supermassive black hole, this effect becomes so extreme that infalling matter doesn't just spiral inward. It gets caught in a whirlpool of dragged spacetime, its orbit distorted in ways Newtonian physics can't explain. Jets erupting from quasars often align with the black hole's spin axis, offering indirect evidence of this cosmic vortex. The Event Horizon Telescope, famous for imaging black holes, has even detected hints of frame dragging in the polarized light around these objects, revealing how spacetime itself is being yanked into a vortex. Then there's gravitational redshift. As light struggles to escape a quasar's crushing gravity, it loses energy, stretching its wavelength toward the red end of the spectrum. This isn't just a subtle shift, it's a dramatic stretch, a direct signature of relativity in action. By comparing the light from the inner edge of a quasar's accretion disk, where gravity is strongest, to light from its outer regions, astronomers can measure how much the black hole's gravity warps the surrounding space. Some quasars show redshift so extreme, their light appears to crawl out of a bottomless well, confirming Einstein's equations under conditions far more severe than anything in our solar system. Even time itself behaves oddly near quasars. According to relativity, clocks tick slower in stronger gravitational fields, an effect called time dilation. From our perspective, processes in a quasar's accretion disk appear to unfold in slow motion compared to the same events in weaker gravity. This isn't an illusion. Time literally passes differently there. When telescopes catch flares or flickers in a quasar's light, those variations are stretched out like a record played at the wrong speed. By analyzing these delays, scientists can weigh the black hole and test whether time dilation aligns with theoretical predictions under such extreme gravity. The most tantalizing tests involve black hole shadows, the dark silhouettes carved out when a black hole's gravity traps light. Quasars with their bright accretion disks act like backlights for these shadows. Simulations combining relativity's equations with quasar observations show near-perfect matches to Einstein's predictions, even in realms where gravity is millions of times stronger than anything on Earth. Yet subtle discrepancies linger, hints that quasars might one day reveal where relativity breaks down and new physics begins. Every flicker, every lensed image, every redshifted photon from these cosmic beacons is a data point in the universe's grand experiment, one that's still confirming and occasionally challenging Einstein's century-old vision of gravity. If you think quasars are just about raw brilliance, think again. These cosmic powerhouses don't just shine. They shove, hurling winds of superheated gas into their host galaxies at speeds so fierce they can reshape entire cosmic landscapes. Picture this: winds roaring at over 20% the speed of light, that's more than 150,000 kilometers per second, blasting outward like a cosmic hurricane, stripping galaxies of the very material needed to birth new stars. This isn't just a gentle breeze, it's a galactic-scale gale capable of shutting down star formation for millions of years. These quasar-driven outflows aren't random. They're the black hole's way of regulating its own growth and its galaxy's destiny. As matter spirals into the accretion disk, the intense radiation and magnetic fields channel some of it away, not just in jets but in wide-angle winds that sweep through the galaxy like a tsunami of ionized gas. Telescopes like the Very Large Telescope in Chile and the Hubble Space Telescope have caught these winds red-handed, spotting telltale signatures of oxygen, carbon, and iron atoms being dragged along at mind-bending velocities. The data is staggering. Some outflows carry enough kinetic energy to rival the quasar's own luminosity, proof that these winds aren't just side effects, they're cosmic sculptors in their own right. What's truly astonishing is the scale. These winds don't just puff away quietly, they can span tens of thousands of light years, reaching far beyond the quasar's immediate vicinity. When such a wind slams into a galaxy's reservoir of cold gas, the raw material for future stars, it heats and disperses it like a blowtorch vaporizing a cloud of frost. In some cases, the wind's force is so extreme, it doesn't just slow star formation, it halts it entirely, leaving the galaxy stranded in a kind of cosmic menopause, unable to produce new stellar generations. Astronomers call this quenching, and it's one of the universe's most dramatic examples of feedback, a black hole's way of saying enough. But here's the twist: these winds might not just be destructive. In some cases, they could actually trigger star formation, compressing gas clouds in their wake like snowplows piling up drifts. It's a delicate balance: too much wind and the galaxy starves; just enough, and it might spark new stellar nurseries at its edges. Observations of nearby quasars reveal both scenarios, suggesting these outflows are as complex as they are powerful. The difference might come down to the wind's speed and the galaxy's gas reserves, a cosmic Goldilocks scenario where conditions have to be just right for creation to follow destruction. The evidence isn't just theoretical. Spectroscopic data from quasars like SDSS J1152+0003 show broad absorption lines, dark gaps in the quasar's spectrum where wind-borne elements have stolen specific wavelengths of light. By measuring how much these lines are shifted, how much the wind's motion has stretched or compressed the light, scientists can clock the outflow's speed with precision. Some readings top 20,000 kilometers per second, with enough force to eject hundreds of solar masses of material every year. Multiply that over a quasar's lifetime, and you've got enough expelled gas to build multiple galaxies, proof that black holes don't just consume, they redistribute, reshaping the cosmos on scales we're only beginning to grasp. Yet mysteries linger. Why do some quasars produce ferocious winds while others seem calm? The answer might lie in the black hole's feeding frenzy, the rate at which it devours matter. Models suggest that the most violent winds arise when the accretion disk is thick and chaotic, like a storm raging at the black hole's edge. In quieter quasars, the disk might be more orderly, its energy radiating away gently rather than powering galactic gales. It's a reminder that even the universe's most violent phenomena follow rules written in the physics of gravity, light, and magnetism, waiting to be decoded by the next generation of telescopes and simulations. So the next time you marvel at a quasar's brilliance, remember, its light is only part of the story. Behind the scenes, invisible winds are racing across galaxies, carrying away the seeds of future stars and writing the next chapter in the universe's epic tale of creation and destruction. They're proof that even the brightest objects in the cosmos cast the longest shadows that shape the universe itself. The future of quasar research burns brighter than the objects themselves, thanks to a new generation of telescopes poised to peel back cosmic mysteries like never before. Leading the charge is the James Webb Space Telescope, with its infrared eyes tuned to the universe's earliest epochs. Unlike Hubble, which glimpses quasars as they were billions of years ago, Webb peers even further back, to the era when the very first quasars flickered to life. Its instruments can detect the faint chemical signatures of primeval gas clouds collapsing into black hole seeds, potentially settling the debate over whether these giants grew from direct collapse or stellar remnants. Webb's keen vision might also spot changing-look quasars mid-transformation, catching them as they switch from dazzling to dim or vice versa, a phenomenon thought to occur when the black hole's accretion disk abruptly refuels or runs dry. These cosmic mood swings could reveal how quasars toggle between feast and famine, a process that's been theoretical until now, but Webb won't work alone. On the ground, the Extremely Large Telescope, or ELT, will bring unprecedented sharpness to quasar studies when it sees first light later this decade. With a mirror spanning 39 meters wider than a blue whale is long, this behemoth will dissect quasar light with exquisite precision, mapping the motion of gas swirling just outside their event horizons. The ELT's spectrographs could even trace the faint glow of stars orbiting perilously close to active black holes, testing general relativity in regimes where space-time curvature becomes extreme. Its adaptive optics will cancel out Earth's atmospheric blur, delivering images so crisp they might resolve the bases of quasar jets, those narrow beams of plasma, for the first time, showing exactly how magnetic fields launch matter at near light speed. Then there's the Square Kilometre Array, a radio telescope network spanning continents, set to eavesdrop on the low-frequency murmurs of ancient quasars. While Webb and the ELT study light, SKA will tune into the faint radio whispers of hydrogen gas stretched and ionized by quasar radiation billions of years ago. This could map the cosmic web in 3D, revealing how quasars sculpted the universe's large-scale structure during reionization. SKA's sensitivity might also uncover quasars' black holes so starved of fuel, their accretion disks have gone dark, offering clues to how these engines shut down. The most tantalizing targets, rare dual quasars, pairs of supermassive black holes circling each other in galactic collisions. Current telescopes struggle to distinguish them unless they're widely separated, but upcoming instruments like the Nancy Grace Roman Space Telescope could spot tighter pairs, shedding light on how black holes merge. Gravitational wave observatories like LISA may eventually detect the space-time ripples from these mergers, pairing quasar light with gravity's own signals for a multisensory view of cosmic violence. And let's not forget quantum leaps in simulation power. Next-generation supercomputers, like those harnessing exascale processing, will model quasar accretion disks in atom-by-atom detail, revealing how magnetic fields twist plasma into jets or why some quasars flicker like faulty light bulbs. These virtual labs might finally explain why a handful of quasars defy the Eddington limit, guzzling matter at seemingly impossible rates without blowing away their own fuel supply. The coming decade promises more than just incremental discoveries. It could rewrite quasar lore entirely. Will we find evidence of intermediate black holes, the missing link between stellar mass and supermassive giants? Could naked quasars, those without host galaxies, prove some black holes wander the cosmos untethered? Each answer will peel back another layer of these luminous enigmas, proving that even after 60 years of study, quasars still hold the universe's most dazzling secrets. Quasars have long captivated storytellers, their unimaginable power and eerie beauty making them perfect muses for science fiction's wildest imaginings. Take the cult classic event Horizon, where a derelict spaceship's experimental drive inspired by quasar physics rips a hole into hell itself. The film's fictional gravity drive taps into the same mind-bending forces that fuel real quasars: twisted spacetime, violent energy release, and the terrifying edge of known physics. It's a horror twist on real science, borrowing the quasar's reputation as a cosmic abyss to ask, what if our thirst for power opened a door we couldn't close? Video games, too, have turned quasars into playgrounds for the imagination. In Destiny, the Vex constructs harness quasar-like energy cores to manipulate time, their radiance echoing the jets of real-world active galaxies. The game's lore even nods to accretion disks, describing singularity furnaces where matter is compressed into raw power. Meanwhile, Mass Effect imagines quasars as natural particle accelerators, their relativistic jets mined for exotic fuels to propel faster than light travel. These fictional takes aren't just eye candy, they're rooted in real astrophysics, stretching quasar mechanics into speculative tech. Even the Warhammer 40K universe features quasar cannons, weapons that channel the beams of dying quasars into planet-cracking blasts, a dramatic if implausible extrapolation of their energy potential. Beyond weaponry, quasars symbolize ultimate frontiers. Star Trek episodes like The Q and the Gray posit them as cosmic gateways, their intense gravity wells serving as shortcuts through the galaxy, a nod to theoretical wormholes. And in Doctor Who, a quasar's light becomes a coded message from an ancient civilization, playing on their real-world role as lighthouses across time. These stories tap into humanity's awe for the unknown, framing quasars less as objects and more as events, moments where science tips into myth. But perhaps the most fascinating twist is how pop culture mirrors real scientific curiosity. Just as astronomers decode quasar light to understand the early universe, sci-fi writers reimagine them as keys to unlocking faster travel, boundless energy, or even contact with other dimensions. The line between fact and fiction blurs after all. Real quasars do warp spacetime, do blast matter at near light speed, and do shine brighter than anything else in the cosmos. The only difference, reality's quasars are stranger and far more violent than any screenwriter could dream up. So next time you spot a quasar in a game or movie, listen closely. Beneath the creative liberties, you'll hear an echo of humanity's oldest question. What if we could harness the universe's greatest forces? Quasars, both real and imagined, remind us that the cosmos is full of wonders and terrors waiting to be discovered. The idea of a quasar pointing its fury directly at Earth sounds like the plot of a sci-fi disaster movie, but rest assured, the cosmos has built-in safeguards to protect us. Even if a quasar were to unleash its full power in our direction, the sheer distances involved act as an insurmountable barrier. Take the nearest known quasar, 3C273, sitting about 2.4 billion light-years away. At that range, its radiation spreads so thin across the void that by the time it reaches us, it's weaker than the light from a street lamp. The inverse square law, the same principle that makes a flashlight beam fade with distance, ensures that quasars, no matter how violently they shine, can't scorch planets halfway across the universe. For perspective, let's crunch the numbers. A typical quasar emits around 10 to the power of 40 watts. That's a 1 followed by 40 zeros, or a trillion times the energy output of our sun. But over billions of light years, that energy dilutes exponentially. By the time it arrives at Earth, it's less than a quadrillionth of a watt per square meter, utterly harmless against our atmosphere's protective shield. Compare that to a solar flare, which can dish out enough radiation to disrupt satellites and power grids right here in our cosmic backyard. In fact, the Carrington event of 1859, a solar storm so powerful it sparked auroras as far south as the Caribbean, released more concentrated energy toward Earth in a few hours than every quasar in the sky combined could muster over millennia. Asteroid impacts pose a far more tangible threat. The Chicxulub impactor, which wiped out the dinosaurs 66 million years ago, delivered energy equivalent to 10 billion Hiroshima bombs, a localized cataclysm no quasar could replicate across interstellar space. Even smaller asteroids, like the one that exploded over Chelyabinsk in 2013, pack enough punch to shatter windows and injure hundreds, a reminder that the real dangers are often the ones lurking unnoticed in our own solar system. The universe is full of spectacular violence, but it's also beautifully self-regulating. Quasars may be the brightest objects in existence, but their brilliance is a distant spectacle, not a death ray. Their light reaches us as a whisper from the past, not a harbinger of doom. So while it's fun to imagine apocalyptic scenarios, the truth is far more reassuring. The cosmos has already rigged the game in our favor, placing these cosmic flamethrowers so far away that their fury fades into starlong before it reaches our tiny, sheltered corner of space. Believe it or not, you don't need a billion-dollar observatory to catch a glimpse of a quasar. Some of the brightest ones are within reach of backyard telescopes and a bit of patience. Take 3C273, the first quasar ever identified and one of the closest to Earth, shining from the constellation Virgo. On a clear, dark night, this cosmic beacon appears as nothing more than a faint blue dot in amateur scopes, easily mistaken for an ordinary star. But that unassuming pinpoint holds a secret. It's not a star at all, but a supermassive black hole's furious glow, beaming at us from over 2 billion light-years away. To find it, start by locating Virgo's brightest star, Spica. From there, star hop using detailed charts like those from the American Association of Variable Star Observers or planetarium apps. 3C273 sits roughly halfway between Spica and the star Beta Leonis. A 6-inch telescope with a good CCD camera can capture its faint light, but what's truly thrilling is knowing that the photons hitting your retina have traveled since the Proterozoic eon, when Earth's first multicellular life was just emerging. The real magic happens when you analyze its light. While stars show smooth spectra with dark absorption lines from elements like hydrogen and helium, quasars like 3C273 reveal something wild. Their spectra are a jungle of emission lines, shifted so far toward the red end of the spectrum that familiar elements become almost unrecognizable. This redshift isn't just a curiosity, it's the smoking gun of cosmic expansion, proof that the universe itself is stretching like a rubber band, carrying quasars away from us at blistering speeds. For those without spectrographs, even spotting a quasar visually is a triumph. Their star-like appearance is a cosmic prank. What looks like a single point is actually the unresolved glow of an entire galaxy's core, outshining billions of stars. Compare it to nearby stars in your eyepiece and you might notice a subtle difference. Quasars often have a steely blue hue, a telltale sign of their scorching accretion disks. Advanced amateurs can push further. Time-lapse imaging might reveal slight brightness variations over weeks, a quasar's accretion disk flickering as fresh matter spirals in. Or try capturing the faint fuzz of its host galaxy with long-exposure photography, a ghostly whisper of stars surrounding the central inferno. Every observation adds to a legacy of citizen science, connecting backyard explorers to the same objects that revolutionized cosmology 60 years ago. The thrill isn't just in seeing a quasar, it's in touching the edge of the observable universe from your driveway, joining the dots between amateur curiosity and the universe's grandest mysteries. Whether you're sketching its position or measuring its redshift, you're not just stargazing, you're time-traveling. Even after decades of study, quasars keep astronomers up at night with puzzles that defy easy answers. One of the most baffling mysteries involves their erratic flickering. Some quasars blaze steadily for centuries, while others dim and brighten like cosmic mood rings over mere months. This isn't just a technical curiosity, it's a window into the chaotic dance of matter near a black hole's event horizon. Imagine dumping truckloads of glitter onto a spinning carousel. Some clumps spiral inward smoothly, while others get flung off unpredictably. That's the accretion disk's reality, where turbulence, magnetic knots, and shocks create flickers that current models struggle to explain. Recent work suggests these brightness swings might trace back to runaway thermal instabilities, pockets of gas overheating abruptly, or even stars being torn apart mid-orbit, flaring like matchsticks tossed into a furnace. But with no telescope yet powerful enough to resolve these tiny, violent regions directly, the debate rages on. Then there's the enigma of the jets, those narrow, seemingly impossible beams that blast matter across millions of light years without spreading out. In lab experiments, plasma tends to disperse like smoke from a chimney, yet quasar jets stay pencil-thin across distances that could span our entire galaxy. The secret might lie in magnetic corsets, helical fields wrapping the jets like taut springs, preventing them from fraying. Simulations at institutions like Caltech show these fields acting like cosmic loom threads, weaving the plasma into focused streams. But observations reveal occasional kinks and bends, hinting at unseen battles between magnetic confinement and external pressures from intergalactic gas. Some jets even exhibit eerie regularity, pulsing like lighthouse beams with clockwork precision, suggesting the black hole's spin acts as a metronome for the entire system. Perhaps the most tantalizing unknowns involve the fuel supply itself. Why do some quasars flare to life after millennia of silence, as if something suddenly opened a cosmic floodgate? One theory points to chaotic cold accretion, clumps of frigid gas, cooled in galactic halos, raining down onto the black hole in sporadic downpours. Others argue for hidden triggers, like distant galaxy collisions sending shockwaves through a quasar's gas reserves. The upcoming Vera Rubin Observatory aims to catch these awakenings in real time, scanning the sky nightly for quasars that suddenly switch on like Christmas lights. Solving these puzzles isn't just academic, it's about decoding the universe's fundamental operating system. Every flicker, every perfectly collimated jet, is a clue written in the language of plasma physics and space-time curvature. And with new tools, from AI-powered telescope arrays to space-based gravitational wave detectors, we're closer than ever to reading the full story. The answers won't just illuminate quasars, they'll rewrite our understanding of how energy, matter, and gravity conspire to build the cosmos. Could quasars be more than just cosmic powerhouses? Could they be windows into realities beyond our own? While firmly rooted in known physics, these brilliant objects occasionally exhibit behaviors that make theorists wonder if they're brushing against something even stranger. Take their flickering, for instance. Some quasars pulse with rhythms that don't quite match conventional accretion disk models. sparking fringe speculation that their light might be interacting with structures beyond our three-dimensional space, perhaps vibrating brains of higher dimensions predicted by string theory. Imagine shaking a sheet and watching ripples move across it. If our universe is embedded in a higher dimensional bulk, quasars' extreme energies might momentarily tug at the fabric in ways we can't yet fully explain. Then there's the curious case of quasars with oddly aligned spin axes. A handful appear to rotate in sync with other quasars billions of light years away, a pattern so statistically unlikely that a few cosmologists have floated the idea of pre-Big Bang imprints or even entanglement across parallel universes. Mainstream physics chalks this up to large-scale structure formation, but the anomaly invites playful what-ifs. Could these alignments hint at a multiverse where universes bubble off from shared quantum seeds, leaving faint fingerprints in their most energetic objects? Even the wilder ideas ground themselves in real math. Theories like eternal inflation propose endless universe birth in a higher dimensional foam, with quasars acting as accidental probes of nearby bubbles. Of course, this ventures far beyond proven science, but that's where quasars become cosmic Rosetta Stones. Their jets, which stay perfectly collimated across galactic distances, might one day test hypotheses like holographic universes, where our 3D reality is a projection of information encoded at its boundaries. If certain jet behaviors defy local physics, could they reflect deeper, higher dimensional rules? Similarly, quasars' redshifts, usually proof of cosmic expansion, have very rare anomalies that a handful of researchers link to light leaking between universe membranes in brainworld scenarios. The key is balance. Quasars aren't proof of multiverses, but their extremes make them ideal testbeds for theories that would otherwise remain untouchable. Every unexplained flicker or oddly aligned jet invites us to ask not just how, but what else, pushing the envelope of cosmology while keeping one foot firmly in observational reality. After all, if the universe has hidden layers, its brightest beacons might be the first to cast shadows from beyond. What if you could play cosmic architect and build your own quasar from scratch? Let's unleash some creative astrophysics. Imagine you're handed a black hole, a galaxy's worth of gas, and the universe's dials to tweak. First, crank up the black hole's mass. Most quasars run on monsters weighing millions to billions of suns, but push it further. 1 trillion solar masses. Now you've got a gravitational titan whose accretion disk could outshine a galaxy cluster. But here's the catch: too massive, and the black hole might swallow matter faster than it can radiate, turning your quasar into a cosmic vacuum cleaner with no showy light display. Balance is key. Next, adjust the spin. A stationary black hole is like a dormant engine, but spin it up near light speed, and you unlock the Blandford-Zenagic mechanism, a natural power generator that twists magnetic fields into high-voltage jets. The faster the spin, the tighter those jets coil, potentially focusing their energy into earth-shattering beams. But beware, overdo it, and the centrifugal force might fling incoming matter away before it can feed the glow. Now, fuel supply. Quasars thrive on chaos, so dump in a galaxy collision's worth of gas, clumpy, turbulent, and rich in metals for that extra radiative kick. Smooth, pristine hydrogen, too orderly. You want a storm of superheated plasma where magnetic tornadoes whip particles into a frenzy, and don't forget the angle. Tilt the accretion disk just right, and you might create a blazar quasar aiming its death ray jet straight at Earth, amplifying its brilliance through relativistic beaming. But here's the ultimate tweak: environment. Place your quasar in a young, gas-drenched universe where filaments of dark matter funnel fresh fuel non-stop. Or trap it in a galactic desert where it flickers erratically as it starves. Each setting paints a different portrait of violence and light. So, architects of the cosmos, what's your blueprint? A modest quasar with steady luminosity, or an unstable beast that flares like a cosmic supernova? Share your designs in the comments. After all, the universe's most dazzling monsters started as someone else's thought experiment too. Quasars stand as the ultimate cosmic power plants, converting gravity into light with an efficiency that puts even the mightiest stars to shame. They're not just distant points of light, they're time capsules. They're beams carrying snapshots of a younger universe when galaxies were still taking shape and black holes were feasting on the chaos of creation. Every flicker, every jet, every redshifted photon tells a story about how matter and energy collide under extreme forces, sculpting galaxies and even shaping the universe's large-scale structure. These luminous giants don't just dominate their corners of space, they influence everything around them, from triggering star formation in distant gas clouds to shutting down stellar nurseries with their ferocious winds. But perhaps the most humbling thought is this. Right now, as you watch this video, light from a quasar that's been traveling for billions of years is finally reaching Earth. Somewhere in the depths of space, a photon that left its accretion disk before multicellular life existed on our planet is just now arriving, a whisper from an era when the universe was raw and untamed. That's the magic of astronomy. Every time we look up, we're not just seeing the sky as it is, but as it was, a mosaic of cosmic history written in light. So the next time you find yourself under a clear night sky, take a moment to wonder. Somewhere out there, beyond the familiar constellations, one of these ancient beacons is blazing away, its story still unfolding across the cosmos. Whether through a backyard telescope or the latest space observatory, we're all part of that story, the universe observing itself, one brilliant quasar at a time.